guess we can start. So welcome to the data integration session. So we have four wonderful speakers. So the first speaker is Dr. Eloyan. She's an associate professor and a vice chair in the Department of Biostatistics at Brown University. She will talk about manifold learning in Alzheimer's diseases. So can you please start?
Thank you for the introduction, and I'm sorry I couldn't be there with you in Chicago today. I will talk a little bit about our work in Alzheimer's disease and some of the data integration issues that we have encountered and the ways that we've been thinking about addressing those questions. So when I started to work in the space of imaging statistics, this was about 14 years ago, and one of the new sort of areas that was emerging at the time were these open access data initiatives. So in some of these studies, the idea was to combine together data sets that were collected in different data collection sites and make those data sets publicly available for researchers to analyze and learn about various diseases and their trajectories. So one of those studies that started in 2004 was the ADNI. So this is different from, let's say, the 1,000 Functional Connectomes project or the ABIDE, where the data were collected for other reasons, but were combined together afterwards. In ADNI, the idea was more to have a unified protocol and have the data being collected in different data collection sites and then combined for analysis. This was focusing on Alzheimer's disease. So as I was working through all of these different data sets, I got a chance to be a part of such an initiative at the start. This was the Longitudinal Early Onset Alzheimer's Disease study that started in 2018. So what is LEAD? So this is a data collection initiative, in many ways very similar to the ADNI. However, the important distinction here is that this is focusing on early onset Alzheimer's disease, where the study participants are diagnosed with cognitive impairment before the age of 65. So this is a very vulnerable group population. Some of the participants that come into this study are in their 40s, are very active, have young families, and so this is a very important, thankfully rare, but very important type of disease to focus on. And what are some of the characteristics of this study? So here, the initial goal was to collect data for 100 cognitively normal participants that entered the study before the age 65. And then 400 participants with early onset amyloid positive Alzheimer's disease and 200 participants with early onset dementia without the amyloid positivity. So this first phase of the study is almost getting close to an end. So the enrollment for the cognitively normal group is completed and the enrollment for the cognitively impaired group is almost done. However, there's space for more opening up the study for enrolling more participants. So that is going to be an ongoing procedure. In terms of imaging, the types of data that we have in this study include magnetic resonance imaging and positron emission tomography. So in terms of the tracers, so PET is imaging modality where the participants are injected a tracer before data collection. And in LEADS, we have the amyloid tracer and tau tracer, and as well as the FDG tracer for the cognitively impaired non-amyloid positive participants. So In addition to that, there is a lot of other types of data. So the cognitive data that is collected through the National Alzheimer's Coordinating Center, or NAC, as well as in the LEADS specific EDC, electronic data collection site, the blood and cerebrospinal fluid, genetics, demographics, pathology, and lots of other types of data. So as can be seen from just looking at this list, and this is by no means the full list, there are a lot of data integration questions that arise when we try to model this data. So ADNI has been around for a while. I'm sure that many of you sitting in that room have worked on the ADNI data already and have encountered some of these problems. So when modeling the imaging data, there are issues of harmonization between the different data collection sites. There are issues with depending on the machine that was used, the technician related potential differences. So all of these issues need to be taken into account. With LEADS, so the one of the next steps for LEADS is the iLEADS, which is international LEADS, where there will be also initially 4 sites added to the study from South America and Europe. So that will also raise additional problems. For instance, the cognitive data will be collected in other languages. So there are questions of how we would integrate that data with our existing data will arise. So what are the important questions? So as I was thinking about this question, what are the main issues that we need to address in the next 5 years? I would say the big one that came to my mind is biomarker estimation. So in Alzheimer's disease, this is obviously important for therapeutics. There are now, when we started LEADS, there were no FDA-approved medications improving that could be used for AD. Now there are. I believe the 3rd one was approved recently. So there are some, but there are still questions of whether they are helpful or not. For example, there is a medication that clearly reduces the amyloid in the brain. The question is this actually translating into cognitive, the improvement of cognitive function? So biomarker estimation, what we mean by this is an indicator of characteristics of normal biological processes, pathological processes, and a response to an exposure or intervention. So in this case, that would be a response to treatment. And that can be from various data collection aspects, so histology, molecular, radiographic, physiologic characteristics, and etc. So in AD research, these are the questions we are asking. The first one that I will bring up is obviously the cognitive performance. So many of you may be familiar with the global cognitive function tests, such as the MMSE, the CDR, or others, ADAS. However, in AD, we are, as is well known, AD is a very heterogeneous disease, and people can have various functions impacted more than others. So in this case, we were looking at cognitive performance in terms of episodic memory, executive function, language, processing speed, visual, spatial. So what we have in LEAD are hundreds and hundreds of cognitive tests that are performed by study participants. So these are pretty messy data, in fact, because the participants may not be able to make it to a visit. This is longitudinal data. There is an issue of missingness, so the participants that get further down in the disease process are just sometimes unable to finish because they're having a bad day, or so there is the informative missingness related to the years since disease onset. These characteristics, so some of the tests have pretty much zero variability for controls. So there are those types of issues that arise when we try to calculate just basic z-scores. So there are a lot of interesting questions here in terms of how to model the data, how to make sense of these data sets. And this is important because a lot of these are used as outcomes when we analyze imaging data. So it is important to have good biomarkers of cognitive function. So of course, we are also looking at trajectories, so time-dependent differences in the cognitive performance, and various types of measures of things that we see on the brain scans. So in this case, these are white matter hyperintensities. So these would be these areas of hyperintensity in the brain. Often people have these white matter hyperintensities as a result of aging. However, as has been shown and as we have shown with the data from LEADS, the white matter hyperintensities are volume is elevated in people who have early onset, especially amyloid positive dementia. And so the question is, how do we characterize these hyperintensities, and how do we model the longitudinal changes in white matter hyperintensities? So atrophy is another important question. So some of the regions in the brain are, when a person has dementia, will atrophy faster than other regions. So it is very important to have the right shapes of the regions so that we can characterize differences between groups. So for example, to address this question, for example, we looked at manifold estimation. So thinking of the brain shape, the shape of these regions as a manifold in 3 dimensions, and trying to model the surface of the manifold using these smooth estimators. The other question is longitudinal scans. So what we observed with the ADNI data was that in longitudinal scans, the segmentation was performed cross-sectionally. So when we were looking at the region over time, we were seeing big differences in the volume, the region increasing or decreasing in size over time, which is obviously not expected to that extent. So we developed a longitudinal principal manifold estimation approach for obtaining these segmentations of these regions in longitudinal scans to preserve the smoothness in time. So this is also very important, obviously, because if we have that much variability in the volume of the region, then it is hard to conduct inference in terms of trajectories for the patient and comparisons between the populations. And the positron emission tomography, obviously, these data are quite different from MRI data sets. So here you can see data for 2 participants. On the left is a cognitively normal participant, and on the right is a amyloid positive AD participant. So the first row is the amyloid scan. So you can see, obviously, the person with amyloid positivity has a much more brightness, so the hyperintensities in the whole PET scan. In the bottom, there is the tau scan. So there are a lot of interesting questions that people are asking in terms of the tau PET and how the distribution of the tau is related to various types of cognitive impairment and how we can estimate that. So this is another, obviously, major area where we need to do a lot of work. So Dana, who I believe is there, has done a lot of interesting work in harmonization of these scans. So how can we even start to analyze the data? We are working on developing tools for pre-processing of the data that will be easy to use so that it can be easier for statisticians to start working with this data. We are also incorporating segmentation of the brain regions, calculation of radiomics biomarkers from these scans, just to kind of support the entry into this space. So PET is relatively new compared to fMRI and MRI that we have, as a research area, have been looking at for a while. But there are a lot of interesting questions here and interesting differences between the questions that we're asking with PET as opposed to MRI and fMRI. So I think I would encourage everyone to kind of think about this data and how we can, learn about AD using this data. So in summary, I think there are a lot of interesting questions in AD, a lot of data where, so I talked about ADNI and leads. There is also Diane, which is a study that is focusing on people who have family history of AD. And there are other interesting studies here, FTLD, all FTLD, which is a dementia study, not focusing on AD per se. So there are a lot of interesting studies, a lot of interesting questions on data integration. And so I think we should be a part of these studies from the beginning to understand the data collection processes and questions, data integration questions, and we should be working more on building easy to use platforms. So thank you very much.
Second speaker, Professor Tanya Garcia from UNC Chapel Hill. She will talk about the missing link, establishing the parallel between censored, covariate, and missing data.
Thank you. Thanks, everyone. Yeah, so I just want to start out by saying I feel really lucky to be part of this workshop. It's been a lot of fun for me getting to see new research directions in neuroimaging and neuroscience research in general, and also just to get to see old friends and meet new people as well. So today I just want to talk about one problem that I've been playing with for a while. And some of the next steps in this problem is linked to data integration. So I just want to lay it out for all of you and maybe be able to get to pick your brains later about possible ways to tackle it. So for over a decade, I've dedicated myself to modeling the progression of a rare neurodegenerative disease called Huntington disease. And for those of you not familiar with this disease, you can think of it as a combination of Parkinson's, Alzheimer's, and ALS. So like Parkinson's disease, Huntington's affects an individual's motor ability, and a common motor impairment is chorea, or uncontrollable motor movement. Like Alzheimer's, Huntington's also affects an individual's cognition, leading to memory loss. And finally, like ALS, Huntington's also affects an individual's psychiatric condition, leading to anxiety and depression. So in short, Huntington disease is a pretty devastating disease, but there's hope. Unlike most neurodegenerative diseases, we know the exact cause of this disease. Back in 1993, scientists discovered that Huntington disease is caused by a mutation in the Huntington gene. That mutation is an unstable repeat of cytosine adenine guanine, or CAG for short. That means that anyone with more than 36 CAG repeats in their Huntington gene has the mutation. So for all of us, what that means is that with a very simple blood test, we can learn if we have that gene mutation. Those with the gene mutation will develop this disease, and those without the gene mutation will not. Now, certainly, the results of that genetic testing can be really heart-wrenching. But from a scientific perspective, being able to identify with 100% certainty who will and will not develop this disease gives us hope. That hope is in the ability to study individuals with this gene mutation years before symptoms even show up. By studying those individuals, we can learn the progression of this disease to find when and how to best intervene. So there's been many different studies to collect this type of rich data to learn the progression of Huntington disease. And one of them was an observational study of about 1,300 individuals with this gene mutation. They were followed for about 10 years. Many different types of data were collected on them. And the plot that I'm showing right now is the symptom severity measured over time. So on this y-axis, we have the symptom severity score, where higher scores mean worse symptom severity, lower scores mean low or minimal severity. And the x-axis is the number of years the individual was in the study. Each of the gray spaghetti lines is the symptom severity measured over time for an individual person. And the dark solid line here, that's the average, or the average of these symptom scores averaged over across individuals. We call that solid black line the average symptom trajectory. So looking at that symptom trajectory, it looks like it initially increases and then decreases, suggesting that symptoms initially worsen, but then get better. That really makes no sense whatsoever, since many researchers have shown that Huntington disease is progressive, meaning it's supposed to get worse over time. And the reason we see this result is because of how I plotted the data. Individuals who enter this observational study enter at different disease stages. Some are more advanced, others are less advanced. And by using this time scale, I'm completely ignoring that information, that difference in disease staging. So there's been many different solutions tried to adjust for those differences. And one of the popular ones in Huntington disease, at least, is instead of using number of years in the study, it's to use the new time scale, years to diagnosis, which I'm showing on this new plot. So here, 0 represents when an individual was diagnosed, -6 is 6 years before a diagnosis, and +4 is 4 years after a diagnosis. So by using this new time scale and shifting these trajectories, we now see a more realistic conclusion. What's happening is that years before a diagnosis, the symptom severity is not so bad. It starts to worsen as we get closer to a diagnosis and continues to worsen thereafter. So we get this more realistic conclusion. But there's a challenge here in that comparing this plot to the previous one, we see a lot fewer gray spaghetti lines in the new plot. And the reason for that is because I did something very bad as a biostatistician. I deleted data. And the reason I deleted the data is because to make this new plot, I had to know when an individual was diagnosed. Because if I don't have that information, I don't know if their trajectory should be over here, or moved over here, or moved over here. And so we need to know that time to diagnosis in order to make this plot. But the problem is that with Huntington disease, because it progresses very slowly over decades, we don't always know that time to diagnosis. So sometimes in these studies, the study will end and an individual will reach the criteria for a diagnosis. In that case, their time to diagnosis is known. But like I said, this Huntington disease progresses very slowly. So often it's the case that the study will end, but the individual doesn't reach the criteria for diagnosis before the study ends. Now, with Huntington disease, these individuals have the gene mutation, meaning they will eventually progress and meet the criteria for diagnosis. So what that means is that even though we don't know when the individual will be diagnosed, we do know it will happen sometime after the study ends or to the right of the study ending. And so in this case, again, the time to diagnosis is not known, but it is right censored. And so this is the problem that led to the statistical problem I've been playing with, which is how can we model this symptom severity score as a function of this time to diagnosis when that time is not known, it's right censored. And this is the problem in the literature that's called the right censored covariate problem, because it's this variable, this covariate X, that is unknown. It's right censored. So when I first looked at this problem, I immediately started thinking, well, gosh, like our field has, there's so many other problems that look very similar to this one. We don't need to reinvent the wheel. Let's try to pull ideas from other fields. And so, for example, a couple ideas that came to mind is this problem looks very much like a missing data problem, because in missing data, sometimes you know X, sometimes you don't. Just like in right censored covariate, sometimes you know X and sometimes you don't. It also looked very similar to traditional time to event analysis, but just with a very simple flip. In traditional time to event analysis, it's usually the outcome that is right censored, not the covariate. But gosh, like it's just a really simple flip of a role of what is censored. Does that really make a big difference? And then thirdly, I thought about, because of the way that people shifted the data, I thought about curve registration or curve realignment, since that's also what's going on. So my team and I, we dug into those different fields to try to pull out methods that we could apply to this problem. But to our great surprise, none of the methods that we tried worked perfectly on this problem, and always some issues would come up. And so by digging into those problems, we were able to identify that although this problem looks very, very similar to other things that our field has studied and well established, it is unique and the nuances are quite small, but they make quite a big impact. Now, one thing I've been looking at is, well, what is that impact? How are people, especially in Huntington disease, where they're trying to design preventative trials, how are they tackling this problem? So what they're doing is they're using an imputation approach. They're developing models to estimate time to diagnosis and plugging in an X. And one of the interests is they want to, once they plug in that X, they build this symptom trajectory model, and they want to test, well, can I slow down the disease? Can I test if a treatment, for example, lowers this slope, because a smaller slope means the symptoms are slowing down. So we checked into that. And so we said, okay, well, what happens when you have a time to diagnosis model that's correct and incorrect? So we're following what the protocol is in Huntington disease. And what I'm showing here on the left here is, how do you estimate that slope that you're going to test if you can decrease? So the dark dash line, that's the truth. And the red box plot is when you use the correct model for time to diagnosis. Blue is when you use an incorrect model. So we see that with the blue box plots, we want to try to get as close to the dash line. It's quite far, meaning it's biased, and that bias persists as you get larger sample size. Okay, fine, we get bias, but does that really matter? Well, it does, in that when you're trying to design what sample size you need to test if you can decrease that slope, if you use that blue incorrect model, you wanted to get 80% power, you would compute that you need about 99 people in your study. But if in fact you use the correct model, with those 99 people, you'd have less than 30% power. So what this slide is trying to say is that, I appreciate my colleagues' efforts to plug in a model for that time to diagnosis X, but it has some pretty substantial consequences. And these consequences carry over into other ongoing efforts right now. So one of the main interests in Huntington disease, and we saw with Alzheimer's as well in our last talk, is that we're really trying to understand, what is this disease trajectory? So if funding and ethics allowed, it would be great if we could actually study what's the progression of the disease in individuals from birth to death, so that we could see the full thing. So that, again, funding and ethics, we could see the full trajectory. But we don't have that. The disease is very slow. There's ethical issues involved. And so instead, what current studies are doing is, instead of getting this full trajectory, we get pieces of it. And what in Huntington disease, and it looks like very similar in Alzheimer's, that studies are recruiting individuals at different disease stages to try to learn the progression. And then the goal is, well, how do you piece together that data so that we can learn this full trajectory, with really the purpose being to know when is the best time to intervene and how to intervene. Now, I'm showing this just very, this yellow line just to represent a disease trajectory, but that you can replace that yellow line with the neuroimaging data. So for example, in Huntington disease, we're also looking into understanding the network in the brain, like how does this gene mutation affect the pathways in the brain network. And right now, people are trying to model, understand that progression in that network after plugging in estimates for time to diagnosis, which I'm arguing is probably not the best way to do it. So anyway, so this is the problem that I'm trying to tackle. The field, other Huntington disease researchers are trying to tackle as well. And I just want to say by saying this is what my lab, the Mind Lab, Methods for Incomplete Data, we're trying to tackle. And it's possible thanks to wonderful trainees and of course, generous funding from the National Institutes of Health and National Science Foundation. Thank you for your attention.
I'm coming from Alzheimer's.
Sure.
I have two-part questions.
Sure.
The first one is, since it's a genetic mutation, do you have family information where you can use the estimated age of onset for their symptoms, like something we do in Alzheimer's disease? That's one question. The second part is, what you're describing in terms of that, time scale or the timeline,
Sure.
independent of the observational study timeline, it's a general problem for any neurodegenerative disease. And one of the things we do in Alzheimer's disease is actually using biomarkers to define the disease timeline. And I believe Huntington disease actually has a biomarker that is used as an endpoint that is approved by FDA, but another thing we do is using short-term observations to build long-term trajectories by something similar to what you suggested, like aligning the curves as an optimum line. Are there any work around that, especially the biomarkers? Like you can, if there's a particular biology.
Yeah, no, let's talk over a break, but just very quick, you're spot on. Those are definitely the directions that in Huntington disease we're pursuing as well. Unfortunately, there is no valid biomarker yet for Huntington disease. So I think you're thinking of the CAG repeat. That's not yet a valid, it's not enough. Yeah, but let's talk more. And other questions as well. Thank you.
So let's welcome our third speaker for this session, Lexin Li. And he's a professor in the Department of Biostatistics at UC Berkeley. He will talk about some recent and ongoing work on intracranial neurodata analysis. So let's welcome.
Thank you. Yeah, let me start by saying thanks, Jan, Hong2, and the organizing committee for putting together this wonderful workshop. It's so wonderful to see and have a drink with so many old friends and also meet new friends. So I'd like to talk a little bit of some of work we are doing about intracranial neurodata. I mentioned at least a few examples, case studies here. Obviously, I'm not able to go into the details, but instead, I'm just trying to give some explanation what's a scientific question of interest here, and maybe one or two slides of our main ideas of our solution. And towards the end, I will try to give my 2 cents on those soul-searching questions Jan and Hong2 posed for all of us. I of course like to thank my funding support and many of my collaborators. So intracranial neurodata, some of you may be familiar with, the others may not. It's, we collect the neurological activities from the brain. What is a little bit interesting here is we actually place the grid or strip of electrodes directly on the surface of the brain. So one of the common modalities we often use is this ECOG data, or some people call this intracranial EEG data. Because of the way we collect the data, it provides very rich sources and also insights about the function as well as the structure of the brain. So it's quite useful in a wide range of areas in neuroscience. So we have been working on a few different aspects of this intracranial data. So one is this so-called brain effective connectivity network analysis during decision making. So simply put, we want to understand how different parts of the brain interact, or one region affects the other during this process of decision making. Another project we are doing is related to this brain, try to understand this brain prefrontal hippocampal pathway underlying approach avoidance conflict. And the last one is this adaptive deep brain stimulation for Parkinson's disease. And the first one, we more or less finished the project. The second one is still ongoing. The third one, we just started with a few ideas. So, so again, each example, I'm just first to try to explain what's the question of interest here. So for the first one, we really want to uncover this directional influence that one kind of a region of the brain has on some other regions, because we all know brain is a highly interconnected dynamic system, you know, and those activities are going to be triggered, influenced by activities of other parts of the brain. So the particular data we are looking at was collected from one epilepsy patient, and we asked this patient to perform some gambling tasks with different levels of winning risk, like high risk task and low risk tasks. During those tasks, we collect this epoch data from 61 electrodes placed in the orbitofrontal cortex area of this patient. And then from each electrode, we collect time series data. So the data is in the format of this electrode by time matrix. The approach, the main idea we came up with here is to use some of these ordinary differential equations to understand this directional influence of one part of brain to the others. So simply put, we adopt this system where xt is like p-dimensional signals in our study, that's 61-dimensional, and we want to understand the derivative of this change of the signal as a function of the signal itself. So our target is this f function in this ODE system, and there's some twist for this particular application that is the data we actually observe is not the signal itself, but a noisy version of the signal. So we observe this y information, which is x plus some measurement error. And once again, the target of interest is this f function, because we would be able to understand one region or one node regulates some other node if those individual elements of the functions have certain forms. Excuse me. In the literature, when we first started to work on this problem, there have been some very interesting solutions out there already. Actually, one I recall was from Tingting. And so people have been developing linear ODE, some additive ODE using some splines idea. And then what we want to do is we want to come up with something a little bit more flexible. Therefore, we adopt this reproducing kernel approach, where we do not explicitly specify the forms of the function, except we only decompose them into main effects, two interactions. Of course, in principle, we can go beyond two interactions, but we typically focus on those first two. So we propose this kernel version of ODE with unknown functions, with noisy data observations, and we also are able to recover the sparse regulatory relationship among these f functions. This would greatly help the interpretation of this identified directed network. And we developed some two-step penalized estimation algorithm. We studied some statistical properties, including the convergence rate, selection consistency, so on and so forth. So that's kind of the first problem we are targeting over here. We did apply, I'm going to skip quite a bit of details, but if you are interested, I'd be more than happy to talk more after the talk. We apply this to this method to this gambling task experiment, and we did find when this patient was performing the low risk games, we found that posterior OFC tends to more actively influence other nodes, as shown from first top panel here. But by contrast, during those high-risk games, which involve more calculations, harder decisions, the anterior OFC tends to be more actively influenced. So this kind of directions tend to be somewhat different under these two types of gambling tasks. Okay. This is the first example or first case study. The second one is dynamic motivated mediation analysis. Our motivation also came from this ECOG study, but it's a different setting. Specifically, this is some work from my collaborator at Berkeley and their lab. One project of their lab was to understand this approach avoidance conflict, or AAC, which describes this daily situation when a single choice enables potential gains or losses simultaneously. And the reason we are interested in this AAC because anxiety can be understood in terms of AAC. And then if we can understand the neurobiology of AAC, it will be very helpful for us to also gain some useful understanding of both healthy anxiety as well as anxiety disorder, such as PTSD. And of course, there are some other applications here. The experiment my collaborators' lab performed was obtained the ECOG measures over 6 particular brain regions of interest. From 15 subjects, each subject performed about 40 trials, and from each region, we collected around 100 time points of measurements. And we have 2 stimuli signals. One measure risk, the other measure reward. And we have the 6 regions of signals. And then we also have an output signal indicating the choice of the approach or avoidance. A particular experiment set up over here is we actually ask the participant to perform this Pac-Man game. Some of you may be familiar with. You have this big face trying to eat dots as rewards in this game. And at the same time, there are also monsters around trying to eat you. So you want to eat dots to be rewarded, but also avoided those monsters, avoided being eaten by those monsters. So the framework we adopt to partly answer this question, what is mediation analysis? So this perhaps many of you are familiar with. We have this exposure or input signals in our particular setting. We have brain signals from 6 regions in the setup. We have this outcome signal, which reflects a choice of the participant. But everything changes over time. So nothing is static, but it is dynamic. We run this over a period of time. At different time points, we have different stimulates, different brain behavior, brain signals, and then resulting in different choices by those individual participants. And so we came up with this dynamic motivated version of mediation analysis. So classical mediation analysis usually focus on a single mediator, but of course there are quite a number of works extending from single mediator to multiple mediators. But then at the same time, we also have this time varying or dynamic nature for our data. So we want to adopt both or extend the classical mediation analysis to both scenarios, motivated mediators and dynamic mediators. And as you can imagine, this problem is not kind of that easy because this mediation effect may come from many other mediators when I focus on a particular mediator, but it could also come from the history, the effects from the previous time points. So we basically propose this approach, this solution, by adopting some ideas from a reinforcement learning. So we introduce a Markov mediation process framework. And then within this framework, we introduce some time-varying linear structure equation models to begin with. Now, of course, we could, in principle, extend this those models from linear to nonlinear version, but we feel even the linear version of the problem is fairly complicated. So we start with this linear one, and then we formally define this mediation effect, the individual mediation effects that is of primary interest. And then when we try to evaluate this, we use this idea of simultaneous intervention calculus from a Peirce approach. And then we study this problem under two settings, finite horizon and infinite horizon. So finite horizon means we have only a fixed finite number of time points. Infinite horizon, in principle, we can have infinite many time points, which is probably more suitable for those dense time points or those dense applications. And then we developed the corresponding estimation approaches, studied some asymptotic normality properties, which also allows us to come up with bootstrap-based inference approach for evaluating those individual mediation effect. So once again, I'm going to skip all the technical details. We have a paper online, we can talk more. This last area is something we feel very excited about, but we just started this adaptive deep brain stimulation. The simple idea here is we place electrodes inside the brain. Here we are looking at the Parkinson patients, and we have found out that by stimulating the brain for those patients, the effect can be very effective to help improve the symptoms of those Parkinson patients. But the current practice is the stimulation is fixed in the sense that in terms of how much amplitude or how strong the stimulation signal stimulate for how long or how frequent, all those things are more or less fixed at this moment. What we want to do is we want to come up with some adaptive solution, adaptive strategy based on those real-time collected data from like Apple Watch or some other devices. And we also want it to be adaptive to individual patients. As we can imagine, one sort of optimal strategy for one patient may not be optimal for some other patients. Again, there are quite a lot of interesting questions. So we are using some different we're developing some different reinforcement learning solutions for this family of problems. But we just started. I don't have that many results to report yet. I'm happy to talk more if you are also working on this. I have a little more than 1 minute. So now I'm going to answer these very, very important questions from Jen Hong too. Many of the previous speakers have given some excellent suggestions, answers, and here are some of my 2 cents from my own experience and my own perspective. I feel some problems are particularly important and interesting. This data heterogeneity, in terms of the individual patient heterogeneity and some other aspects of heterogeneity. And this brain stimulation, I think, is also very important. We start to stimulate the brain or to introduce some intervention to the brain and see what's the outcome, what's the reaction. I feel that's very, very important. For the second question, I do feel, if we can, it's related. So it's if we can create a high quality benchmark data sets, and finally, go to neuroscience conferences. It's one possible helpful way to answer some of those questions is to welcome to submit your high quality papers to the Annals of Applied Statistics, partly because I think this is a very nice outlet promoting high quality work, bridging statistics, biostatistics, and different applications. And partly because I'm the incoming editor-in-chief for this journal next year. So welcome to send your papers there. But also we do, thank you. We do plan to introduce some new components to this journal. For one thing actually is we are thinking to create a new subtrack for benchmark data set. We all know benchmark data is really, really useful. Maybe this ImageNet created by Fei Li is a wonderful example. So we want to have an outlet for you if you have, I know, like Tingting mentioned yesterday and Martin mentioned as well yesterday, you have spent a lot of efforts creating this wonderful data sets. So we want to have a good way to recognize your efforts, but also I believe this would greatly benefit the community. both statistics community and eventually neuroscience or application areas. Okay, I will stop there. Thank you very much.
So our fourth speaker is Professor Hai Shu from New York University. And he will talk about the orthogonal common source and the distinctive source decomposition of high-dimensional data views. Let's welcome.
Thank Dr. Zhang for the nice introduction, and thank you the organizers, the speakers, and the audience for this wonderful workshop. Hello everyone, I'm Hai Shu from NYU. I will talk about my recent work on orthogonal common source and distinctive source decomposition between high-dimensional data views. So first, let me introduce the background. As you know, nowadays many biomedical studies collect multi-view data. For example, the HCP project has multi-module brain image data like structural MRI and the functional MRI. And also the ADNI project has both genomic data and image data. Let's look at this data structure of multi-view data in detail. Suppose we have K data matrices, Y1 to Yk, and each data matrix represents their type. And the variable dimensions of this data matrix can be larger than the sample size n. So it's a high dimensional data problem. And for example, for the Y1, we can let it be the ROI, the PET image data from n subjects. And the Y1 and the Y2 could be the SNP data from the same set of n subjects. So a popular model is to decompose each matrix Yk into 3 parts: a low rank common source matrix Ek, a low rank distinctive source matrix Dk, and noise matrix Ek. And here X is the low rank signal matrix, that is the sum of Ck and Dk. So our goal is to decompose Xk into Ck and Dk, the common and the distinctive part. So in this popular model, all those common source matrix K are assumed to be generated from the common latent factors of these K data views. And the distinctive source matrix Dk is assumed to be generated from distinctive latent factors of the corresponding case data view. Assume the columns of this data matrices are an ID samples of corresponding mean zero random vectors. Okay, so there are many methods to solve this decomposition, but they are different in defining the common and the distinctive latent factors. Okay, so here I just listed the 9 methods that are widely used or recently published. So these methods have a common drawback. They fail to well consider the orthogonality among the common latent factors and distinctive latent factors. So here the orthogonality means the uncorrelatedness. Okay. Some only consider the orthogonality between common latent factors and the distinctive latent factors. For example, the famous stripe method. Some only consider the orthogonality between distinctive latent factors from different data views. So we can see here we have 2 types of orthogonalities. One is between the common latent factors and distinctive latent factors. The other is the orthogonality between distinctive latent factors from different data views. Even so, some methods consider both types of orthogonalities, but either sacrifice unexplained signals as noise, like the Alzheimer method, or give an asymmetrical decomposition for identically distributed signals, like the slide method. Okay. So a question: why do we want the orthogonality constraint for these latent factors? Okay, what's the benefit? Because this orthogonality ensures the complete separation of these latent factors. Okay, say for example, here say we have 2 latent factors, F1 and F2. Okay, they can either one is common, the other is distinctive, or both are distinctive latent factors. Okay, if they are correlated, okay, we can always project F1 onto F2. Then we can get this equation, right? We can get this equation. So we can see F2 may be viewed as the common latent factors of F1 and F2. So we want to impose the orthogonalities between them to ensure complete separation of common and distinctive latent factors. Okay. So our goal is to well define those common and distinctive latent factors with this orthogonality constraint. Otherwise, the subsequent data analysis is not correct. Okay, so let's consider a simple case. Okay, say here we have two standardized random variables D1 and D2 with non-negative correlation low. Okay, if they have negative correlation, we can consider negative D1 instead of D1. Okay, we want to decompose the D1 and D2 into a common variable C and the two distinctive variables D1 and D2. Okay, could anyone suggest a good way to do this decomposition? Okay, so let's look at the previous methods. Okay, so we'll give these three solutions. So solution 1 is not good because you can see C is always 0 when D1 and D2 is not equal. So that means even they have a large correlation, the common variable is always 0. And solution 2, in solution 2, you can see even though C is orthogonal to both D1 and D2, but D is equal to negative D2. That means D1 and D2 share the same latent factor, just that their directions are opposite. Okay, and for the solution 3, we can see C is not orthogonal to D1 and D2. Okay. So we can see these three solutions do the decomposition within this two-dimensional space spanned by D1 and D2. Okay, but our goal is to want to have these three random variables C, D1, and D2 to be mutually orthogonal. Okay, so as you know, in a two-dimensional space, it's impossible to have three mutually orthogonal non-zero elements. So we need to expand this two-dimensional space to three-dimensional space for our decomposition. Okay, so here we propose our method called the DCDLF method. So we do this decomposition in a three-dimensional space spanned by D1 and D2 and a new variable orthogonal to D1 and D2 in this three-dimensional space. Okay. So we can in this three-dimensional space, we can guarantee the orthogonality between C, D1, and D2. And this orthogonality is unique if you have this third axis. Okay. And one impressive result we have is the variance of C is equal to the correlation of D1 and D2. Okay, D1 and D2. Recall that D1 and D2 are standardized random variables. That means they have a unit variance. So this result means the variance of D1 or D2 explained by C is equal to the correlation. Okay, equal to the correlation. And the variance of D1 or D2 equals 1 minus rho. Okay. So you can see the norm or equivalently the standard deviation of C increases when the correlation of D1 and D2 increases. Okay. For high dimensional cases, we can use the CCA method to decompose the spaces and get the canonical variables. And as you know, these canonical variables form the orthogonal basis of the respective signal spaces. So we can write the each xk as the linear combination of these canonical variables. Okay. And since each pair of those pairs of canonical variables are mutually orthogonal, so we can do this simple decomposition within each pair of canonical variables. Then we can plug in this Z this z equal c plus d into this equation, we can obtain our decomposition. Okay. But here we have one issue. Okay. Because this decomposition is not unique, because one can arbitrarily choose one variable orthogonal to Z1 and Z2 to form this three-dimensional space. So this decomposition is not unique. But here I want to say, even though this decomposition is not unique, but our method provides a unique decomposition of the covariance matrix. Okay, and here our matrix satisfies this rule of thumb. Okay, so that means the covariance of xk equals the covariance of C plus the covariance of D. Okay, and also the proportions of the signals variance explained by the common source vector CK and DK also satisfy this rule of thumb. Okay, so this is the method. So if you are familiar with PCA, okay, so this method is kind of parallel to PCA, but extended for multi-view diagnosis. So let me give you a real diagnosis to illustrate our method. Here we got data from the ADNI project, and we have the PET image data and SNP data. Okay, here we have 120 ROIs and 397 SNPs. Here we have Alzheimer's disease group and the normal group. So within each group, we do this decomposition, okay, for this true view data. Okay, so here we have the result got from our decomposition. So the first row shows the correlation matrices for the cognitive normal group, and the second row shows the correlation matrix for the Alzheimer's disease group, and the third row shows the social difference. Okay, so we can see the common source vectors provide more distinguishable correlation matrices difference between these two groups, especially in the top left block, this top left block. Similarly, for the SNP data, we can see our common source vector C provide a more distinguishable difference between these two groups. So for example, this bottom right block. And also, we can plot out the proportion of variance explained by these common latent factors. And then we can see the difference between these CVP values between these two groups. Okay. So that means we can use this new data from this decomposition, because this decomposition gives us the common source matrices and the distinctive matrices. These are new data. And this new data provide extra information and the patterns to distinguish the two groups. And also for the questions requested by Dr. Kang, so here is my answer. Okay, so so I will focus on the problem of data integration. For example, extend our DCDLF method to linear cases. So as you know, this decomposition now is for the linear cases, because it's a combination of those latent factors. So I want to extend it for nonlinear cases. For example, replace the orthogonality with the independence. Okay, independence. So replace the uncollinearity by the independence criteria. And also for the how to improve the processing of data sets. So it's I would suggest to share your computer code on GitHub, because it's very important to other researchers to use a computer code for comparison, to benchmark work. Okay, and also how to make a statistical method to manufacture in imaging community. So my collaborators always tell me nowadays all the radiologists use deep learning methods, the AI approaches. Okay, so one suggestion is to combine statistical method with deep learning method. For example, here we can replace the linear CCA by deep CCA, and in our framework. Thank you.
I finish within 40 minutes. Any question for Hai first? No? Okay, we can move on to the question and answer session. So we should first let Tanya finish her answers to the question. I'm also curious why Huntington does not have a biomarker. They already have genetic differences.
Because it's extreme. Yes, we have these genetic differences, but there's still a search for biomarker. I mean, it's still a really difficult disease despite this genetic information.
Well, it doesn't tell you about the progression.
It partly does. Yeah, so that's the challenge. So the gene was discovered in 1993. We thought, or excuse me, the field would thought a cure would be found within 5 years. But as they were accounting for that genetic mutation, they found that it only explains up to a point, and there's still so much unknown. And that part of that unknown is the lack of biomarkers.
Can we just check the genes?
You mean like other genes, or? Yeah, that's been explored as well, and you know, some advances have been found, but not fully yet.
Is there any data on like the expression of the genes?
Yes.
If they born with a gene, there must be a certain blend or something that makes them express.
Exactly.
clinically.
Yeah. The challenge is the field still doesn't understand what exactly that mutation does. And so it leads to some like a mutated form of the Huntington protein, but exactly what effect that has, it's unknown. So like they've tried, you know, let's just cut it out completely. Let's just get rid of that, kind of like with CRISPR approach, just get rid of it. But that led to some negative consequences. So they don't know how much to cut, how much, because it has some benefits as well that they just don't know
Yeah,
yet.
just going back to my first question,
Please.
is this familial?
Yes.
So do
Yes.
they have that family history information regarding at what age that the parents, that the carrier develop the disease? And
Right, so there have been some family studies. It's a study called Cohort. And yes, that has been explored. But then there's also, yeah, I mean, it has helped to bring some new knowledge, but I guess I'm saying the same thing, like there's still so much unknown,
what
unfortunately.
is the primary outcome? Like, what is the primary clinical measure in clinical trials?
Yeah,
How does
so
that work with
that's
FDA?
that's a really good question. So right now in the clinical trials, they're using mostly something called total functional capacity. So it's a score that measures how well it's like how well you can behave independently. But then that's been like the standard in the field. There's been a push to saying, hey, it's not just about functional capacity, it's about motor, cognitive, psychiatric. So then they've been trying, like in Europe, they have like a combination of outcomes that have been tried in clinical trials that hasn't been tried yet in the US though.
Just one final thing. It's just a couple of years ago, I believe FDA, it was the first neurodegenerative disease where FDA actually approved that biomarker outcome, and I believe that was Huntington disease. Do you know what was that biomarker?
That's a good.
I think it was an imaging biomarker, and it was a big deal because
Let's-
that's the first in neurodegenerative
Yeah,
diseases.
please, I'd love to hear it. Maybe I totally missed it also.
One quick question too. Yeah, I guess we're not going to hear a different story on the biomarkers, but from a clinical perspective, is there something that we see in patients at this stage? Because obviously it has a long program of patients like AD. So what about just before onset?
Yeah,
Is there
yeah.
anything we see in terms of shift?
Absolutely. So about, I think 8 to 10 years before, we see changes in cognitive measure. And so there's been a push to like use that as a measure of onset. But I'm not sure how it is in AD, but like my understanding is evaluating cognitive changes is really difficult, like very sensitive. And so there's been that challenge as well. I don't know if that's the same at AD. I'm guessing it is.
In AD, we have lots of biomarkers, so we're
Oh,
a
do
little
you?
bit
Oh, that's
spoiled
wonderful.
from that.
But they don't
perspective.
always correspond to clinical assessments though.
I see.
So
Heterogeneity, right?
Yeah.
I'd love to talk more.
Any other questions for other speakers? Okay, I want to have a question for Anya. So
The results are very interesting. So I'm curious how you combine the hippocampus shape changes with the other imaging data. So you actually examine the temporal changes. So how you combine all this together?
So, so far we have looked at the extraction or the segmentation of the hippocampus. So this method is estimating the smooth surface of the hippocampus over time from the longitudinal MRI scans specifically. So in terms of like putting it together with other types of data, so far it's mainly just like a summary measure based. So we look at the effects. So is there, for example, difference in the trajectory in the tau PET once you control for amyloid, something like this. But as we sort of obtain the segmentations, the next questions are, using these segmentations, how are we going to add the PET scan data and kind of characterize these changes? For PET scans, we are looking at different questions related to the tracer uptake. So it's a more of a texture type question rather than a shape question. But that's kind of an ongoing work we are looking at right now.
Thank you. Okay, I guess this is a perfect time to
Conclude the session. It's a long talk.
Let's thank our speakers, please.